Maybe the lights on the back.
Yeah, let me
Probably off, yeah.
Okay, so we'll go ahead and get started. Greetings, everybody. Thank you for joining us for NOAA AML's Physical Oceanography Division Seminar Series. You all probably know our speaker, Dr. Hosmay Lopez. Hosmay is going to be talking to us about the East Asian monsoon as a modulator of U.S. Great Plains heat waves. If you don't already know this about Hosmay, he got his PhD in 2013 from the University of Miami. He's been working here through CMIS since 2014. For those of you listening online, you'll have an opportunity to ask questions, but please remember to mute your speakers while Hosmay is presenting. And Hosmay, when people ask you questions, if you have a chance, try to rephrase the question before responding so that people online will get the message.
All right. Well, good morning, everyone, and thanks for coming. Please feel free to get some cookies because with this lighting and the topic, you may as well fall asleep. So today, like the title suggests, I will be talking about a recent paper that was published online today, this morning. So good timing. This work was in collaboration with several scientists here at AOML, Sanki Lee, Shenfu Dong, Gustavo Gonib, as well as our former lab director, Bob Atlas, and CMAS director, Ben Kertman, and Arun Kumar from CPC. All right, let me click on them. So the outline of the talk is I will give you a brief introduction of extreme events, namely heat waves, and I will talk about why we care about heat waves, why we study them, and I'm gonna present about the methodology we use to study heat waves, including the models, observations, and model experiments. And also I'm gonna introduce how we detect heat wave, how we define them, and how we assess their future projection on their anthropogenic climate change. And also we're gonna assess the relative role of natural variability versus anthropogenic forcing in the occurrence of heat waves. And also we're gonna identify naturally occurring drivers of heat events. You've probably seen this slide before in previous presentations, but I can't stress how important these heat waves are. This is from the natural hazard statistics, which shows that extreme heat is the #1 weather-related cause of death in the US. And they list several extreme events. This is their definition of extreme events. And I can see a young future scientist, let's say a kid from middle school, high school, thinking about becoming a geoscientist, weather oceanographer, meteorologist, thinking about, yes, I want to be let's say a meteorologist because I like hurricanes, or I like tornadoes, or I like studying rip current because I cannot swim on the beach, so I want to know them. But I cannot see any middle high school kid thinking about, oh, I want to be a meteorologist because I want to study heat waves. Because these extreme events, even though they're very important, they're very boring. So you get very little scientists trying to attempt to understand their mechanism. And there are great scientists out there studying these extreme events, but there are a few. And even this is the only extreme event that's very large scale and very persistent in time, but still not well predicted. So that goes against our knowledge of predictability. If something is large scale and persistent in time, it should be predictable. Guess what? This is not predictable beyond your typical weather forecast that you see on the news. So I think this is one very important extreme event that we should take a look at. And in future climate projections, there are studies saying that heat waves, there's very clear signal that they're going to become more extreme and more often under anthropogenic climate change. And that's obvious, right? You have a warming temperature, heat waves, it goes along with it. And you see that in that study by Mail et al. That shows that the ratio of extreme heat versus extreme cold keep increasing into the 21st century. And actually, we are right now into a 2-to-1 ratio of how often we have extreme warm versus how often we have extreme cold. And these are some examples of some of the deadliest extreme events in the past 30 years. And you see some of them are outrageous, the number of fatalities associated with them, like the European heat wave in 2003 and the Russian heat wave in 2010. We also had some extreme heat waves, recent ones, back to back in 2 years, 2011 and 2012, in the Great Plains of the US, which were associated with hundreds of deaths, well above their average, long-term average of 123 deaths. So this, on top of those, this is our very extreme events. And I'm going to concentrate on these two, 2011 and 2012 events, and I will show you how extreme they were. And this is on the top panels. Well, the left panels are for the 2011 event, and the right panel out for the 2012 event. And these are for two cities in the Great Plains, Oklahoma City in Oklahoma and Dodge City, which I don't know what it is, but it says it's in Kansas. But you can see that what it shows is the smooth lines, the green and blue, are the annual mean, maximum and minimum temperature. And the contour about this smooth line, the green shading and the blue shading, are the 95th percentile, both above and below. And on black, what you see is the black line is the actual temperature for that year, high and low. And shaded in red is what's shown temperature instances where that temperature exceeded the 95th percentile. You see that for Oklahoma City in 2011, there were over 50 days where temperature exceeded the 95th percentile for that summer. And this is a place where the summer temperature is very extreme already. So this is a very extreme, long persistent event. And also for the Dodge City case, those numbers in the bars for each month is the number of days for that month that exceeded the 95th percentile. So you can see in July, 14 days exceeded the 95th percentile. That's very extreme too. In the middle panel, what I'm showing you is, in the contour is the 500 millibar geopotential high, no anomaly, just the high, although it looks like an anomaly. You can see a very strong ridge anticyclone over the Great Plains in both locations, outlined by the green triangles. And on the bottom is just the seasonal mean for that summer specific temperature anomalies. You can see for the seasonal mean, the anomalies is 6 degrees Celsius. So that's a very extreme anomaly. Of course, that's basically what we say on the top panel. But you can see the bottom panel is significant because you can see the magnitude in scale-wise of these events. These are 1,000 kilometers events. And they persist for so long. So we want to understand what's really driving these extremes in the Great Plains. And there have been studies that shows that SST anomalies in the tropics, which are often linked to teleconnection patterns and weather modulation in mid-latitudes, were not associated with these extreme events. And that's bad. That's a bummer, because SST anomalies are probably one of the best predicted variable in the climate system. So it will give us some lead time to understand these events. And this study said that it was just due to internal atmospheric variability, which basically doesn't have any much predictability beyond the 7-day time scale. So we want to understand a little more what's driving these things. This is just to show you how extreme these events were as well. 2011 over Oklahoma and 2012 over Kansas. This is a temperature profile. This is what's called a SQT log P diagram. It's just a thermodynamics diagram of the atmosphere. And what is shown in the vertical is the pressure level in a logarithmic scale. And in the horizontal here, skew towards the upper right is temperature. And the red line here will be your temperature readings as a function of height. And the blue will be your dew point reading. So basically the moisture variable. And what you can see is dew point and temperature are far away from each other. meaning it's very dry. And you can see that at the surface, you have readings of almost 45 degrees Celsius in temperature, whereas the dew point is only 4 degrees Celsius. So the relative humidity there is almost zero. So this is how extreme these events are. Also, you can see that from the surface up to about 700, 600 millibars, the temperature line follows, this is called potential temperature line. It follows basically the dry adiabatic lapse rate and follows the potential temperature. And also the dew point line follow these dashed lines, which are the mixing ratio lines, meaning that temperature and humidity are fairly constant in a very deep layer in this near surface atmosphere. You're talking about layers as deep as 3,000 to 4,000 meters, meaning that there is tremendous mixing from below because of the surface heating, enhanced surface heating. Also, you see the wind pattern. This is just a wind profile. It's fairly calm throughout the atmosphere, meaning that the weather is stagnant. So you will see that in a pattern like this, it tells you that this extreme weather will persist for a long time because there is no circulation anomalies that will take it away from these regions. And also you see that the dew point line, this is the dew point temperature line actually decreases above that well-mixed layer, meaning that there's a strong subsidence, a strong sinking motion, and persistent because of an upper level anticyclone, which I'm going to show you. So in all, a very extreme case. This is a movie for the 2011 case. And on the bottom, these are schematic diagrams of stagnant weather, what we call blocks. One is omega block, a split flow block, high over low, and as well as a cutoff high. These are typical blocking patterns which persist for a long time associated with heat waves. The most common in the summer are the omega block and the cutoff high. The two middle ones are often more common in the winter. But you can see oftentimes in the movie up there, you can see the omega block pattern developing in those days. Oh, there's a hurricane going by. And that wasn't intended, by the way. I was surprised. What is this? And I had to Google, oh, that's a hurricane, and that was Hurricane Irene in 2011. So you see several instances where there's one where there is an omega blocking pattern there, which then becomes a cutoff high pattern, loses the two low pressures, starting the high pressure, and just become something like this that persists for a long time. I will show you an example of the 2012. It's probably more dramatic. Right there, that's an omega block, which then becomes a cutoff high. And this is very important because these are weather patterns. Unpredictable after 10 days. And these are the main drivers of heat waves. And these patterns sometimes persist for weeks, and you see even months in the 2011 case. And the reason is because this high pressure pattern has very little dissipation going against it. The only dissipation that this high pressure pattern, a cutoff high like this, will have is radiative cooling at the upper level of the atmosphere because of clear sky. And that's a very slow process already. So they tend to last, yes?
Just wondering, is there a difference in persistence between the different blocks?
These often are more persistent in time, the cutoff high. The omega block persists for a few days, but it tends to lose the two lows as starting the high, because with the two low pressures, these are upper level patterns. With the two low pressure, they undergo dissipation much faster. Once they are small scale, the pressure gradient is stronger, the static stability is weaker, so the vertical momentum flux is higher in the low pressures, which induces surface friction, and that's one way to actually weaken the lows. And also diabatic heating. You have a low pressure, you may have convection, and diabatic heating below a low pressure, upper level low, will diminish the low, will dissipate it. And what it ends up with is with something like this. So it loses the two lows as starting the high pattern, and that becomes more permanent because you only have basically one dissipation component. And friction is very small because you see on the profile the wind pattern is very weak. So you can see, last 4 weeks, even months. And what I'm showing here in color is a potential temperature at the tropopause level. So this is at the level of the temperature invection in the atmosphere. You see very high potential temperature, meaning either the layer is very thick or below this level, the layer is very warm, or a combination of both. So now that I gave you an introduction, long introduction on the two events, I will give you the goal and objective of this study is to develop, the overall goal is to develop a seasonal and subseasonal prediction system, and also interannual and multi-decadal prediction system for extreme heat and drought in the US. And the objective to achieve this goal is first to identify the common patterns of heat waves, which before our study in last year hasn't been done for the US. We want to quantify the relative role of natural variability versus climate change with respect to heat waves. And also we want to identify with those, once we identify the relative role, we want to find natural occurring forcings for this heat wave, which will enhance our predictability abilities for these cases. So for the methodology, we're going to use observations, basically reanalysis from the European Center, from medium range weather forecast. This is the 20th century reanalysis. I have done several validation of this reanalysis and others, and this is the one that actually fit my model the best. So my model looks like this reanalysis, either both are wrong or something is right there. So that's why I choose this reanalysis. I'm going to use precipitation reanalysis from GPCP, as well as diabatic heating from the Japanese 25 reanalysis. I'm also going to use model for this study because even though the ECNWS reanalysis span 100 years, it's still kind of short to analyze extreme events that only occurs once in a while. So in that reanalysis, I only have a few events. So I'm going to use a couple model with thousands of years of pre-industrial simulation, 30 ensemble members of 200 years length in 20th and 21st century projections. And also I'm going to use a CIMIT-5 prediction and projection as well. And also these models are becoming so complex these days that it's very difficult to understand the basic physics. So we want to rely on something simpler as well. And that's why we're going to use a linear baroclinic model from Watanabe and Kimoto. This is a dry GCM, general circulation model. It's much simplistic than the couple models, but they're still complex. It has it's linear, but it allows for wave-wave interactions. So it's not that simple. And we're gonna analyze all this data. We're gonna define heat waves. I think I showed this slide once before, but I think I have to show it again. We're gonna define the heat waves in a very discriminative way. We're gonna define it. We're gonna use temperature threshold. Only we're gonna keep the temperatures that are above the 95 percentile. Everything else will be set to 0. We're gonna do a spatial smoother by applying a moving window to remove hot grid points, which are no heat wave-like. Heat wave are large scale. We're also gonna apply a temporal smoother. So this stream will have to persist for at least a minimum of 3 days. And at the end, after these first 3 steps, we're gonna have maps of streams, anomalies, which are only positive definite, only above the 95 percentile, and everything else will be set to 0. To those maps, we're gonna merge it into events using, and I'm not gonna try to spell out this methodology, I'm just gonna call it clustering algorithm. And we're gonna merge them into cluster-like events. So if you have 2 heat waves comprising of several days, we're gonna find the correlation, map correlation, spatial correlation of these maps. And we're gonna merge the 2 events that look more alike. And we're gonna do that multiple times. If, for example, for the couple model case where we have thousands of years of simulation, we may have hundreds of maps. So we're gonna start merging them and working your way down to a single map. That single map will define you the global heat wave, or at least the North American heat wave. But you don't want to do that. you want to have a stopping criteria, and that's called the dissimilarity index, where you start merging all the way until the dissimilarity index reaches a maximum. Beyond that, it starts decreasing again, meaning that you're merging two events that they don't look alike. So at that maximum point, you have reached the optimum number of clusters. And that clustering algorithm will provide you a spatial map and also a time series of temperature, maximum temperature, duration of the events, and all that. And this is from our 2018 paper. We found the optimum number of clusters to be 8, but only concentrated on the 4 that influence the most population over the US. And these are the 4 clusters: Great Lakes, Northern Plains, Southern Plains, and Western US. And what we found was striking, that under climate change scenario, the future projection of this cluster are different. Even though they're in the same country, their future projection is different. We found that for the Great Lakes and the Western US, climate change influence on the cluster of this type of heat waves is very certain. So natural variability will be secondary in terms of importance. But we found for the 2 Great Plains clusters is that natural variability, even under the most pessimistic climate change scenario, the RCP 8.5 scenario, will be dominant well into the 21st century. And these are the 2 regions where we found the very extreme heat waves lately. So we want to understand what's driving the natural variability of these extremes. This is from ensemble spread. We have multiple model projections for the 20th century and 21st century. And we computed the ensemble spread. It's just the difference between each ensemble member. That's an estimate of natural variability. And this is for surface temperature, and what we found is very clear-cut pattern of Great Plains uncertainty, both in the 20th century and 21st century. And for the 21st century, the uncertainty is even larger than in the 20th century. So natural variability is projected to increase in the Great Plains as well. And this is again from our 2018 paper, the 4 clusters. And what is hopefully you guys on the back can read the axis. This is time in the 21st century, starting in 2015 all the way to 2095. And the y-axis is the fraction of heat wave events that are attributed to climate change. And what you see in the 2 lines is just the projection for the 4 clusters. You see that for the Western US, at this moment, about 40% of the heat wave could be attributed to climate change. And climate change will be the dominant driver. That's the dots above the dashed horizontal line at 50%. So climate change will be the dominant factor for at least half of the heat waves as soon as the next decade in the Western US. But for the Great Plains, this doesn't occur well into the 21st century, up to 2070s for the Southern Plains. And it is striking that I see some decadal pattern in that future projection. And this is just the time of emergence. This is a derived quantity. This is not coming straight from the model. This is derived from a PDF analysis. And you even see a multi-decadal oscillation in the Southern Plain for the future projection. So these 2 Great Plains heat waves future projection of them are uncertain because of large natural variability. We want to understand what's driving it. Going back to the 2 cases, 2011, 2012, you see the spatial pattern on the top. And in the middle panel is just a heat wave cluster that comes out of the cluster analysis from observation and from the CSM model. See, they're very, very similar in pattern. Even you get the negative anomalies over the northwestern US. So it's very striking that these 2 events fits very well with this Great Plains cluster. And we did a composite analysis and look how does the large-scale atmospheric circulation are associated with those clusters from observation and from the CSM model. And you see kind of like a wave number 3 pattern, trans-Pacific wave number 3 pattern. What's showing is a stream function, positive means kind of anticyclonic in this case. And the vector is the wave energy flux. This is where the wave energy is coming from. And seems like a wave number 3 across the Pacific. So I think there is some potential for predictability if we can actually identify what's driving this teleconnection pattern. This is same for the 2011, 2012, JJA on top, and June, July, and August on the bottom, precipitation. And was striking, and this is precipitation anomaly, interannual anomaly. What's striking is that, especially for June, those anomalies over the southeastern Asia looks very similar to what's known as the East Asian monsoon. So you also see over the Great Plains drought anomaly associated with the heat wave. So we think that this teleconnection pattern, wave number 3 pattern, may be forced by this convection over the East Asian monsoon. And that's our hypothesis, and we want to test it. Same again, this is a composite during the heat waves, but now this on the top panel is the vertical component of the wave activity flux. That arrow I showed you earlier, that's the horizontal component, the two components here, zonal and meridional. What I'm showing you here is the vertical component, and you see that there's a common region over East Asia, Japan, that shows you upward wave activity flux. This is indicative of convection and could actually force this teleconnection pattern. On the bottom, this is a cross-section across those, but now looking at the wave source, this is Rossby wave source. The first term is vorticity advection by the divergent wind. Divergent wind denoted here by V chi. And the other term is vortex stretching by the divergent wind. And you see that over the East Asian region, there is enhanced wave source. And the positive color indicates source for anticyclone. The blue indicates source for cyclonic waves. So you see there is a source for anticyclonic wave over the East Asian monsoon at the upper level of the atmosphere. So I think we have identified a potential source. Now we want to run a very simple linear baroclinic model using this hypothesis. What I'm showing you here is just the precipitation associated with the East Asian monsoon in the top panel A. In the panel B here, the contour is the zonal wind. You see a zonal jet stream there. And the color is the diabatic heating rate, which looks very similar to the precipitation, because the precipitation is mostly driven by convection. So this convective diabatic heating rate is very similar. And the panel C shows the vertical profile on top of that monsoon region, and the wind, zonal and vertical wind. And here panel D shows that this heating profile is your typical mid-level profile associated with tropical heating. And on panel E, what is showing is the jet core and the heating rate. So we want to prescribe on this linear baroclinic model, which only needs to be prescribed. What you only need to be prescribed is the background state, which includes zonal meridional wind. This is your background state, temperature, specific humidity, and surface pressure. And we will force that linear baroclinic model with these heating anomalies that you see in the contours associated with the East Asian monsoon. And we're going to run this model in a steady state sense. So we're going to run it until steady state solution is achieved, because this is a teleconnection pattern often associated with the stationary waves. And the transient component is too complicated to analyze. But we're going to allow wave-wave interaction. So the background state is allowed to vary in the zonal sense. And this is the solution using the background state as June, July, August, and also using background state for independent months, because it matters. What we see here again is wave number 3 pattern, just like I showed you before, associated with the heat wave. You have a very strong anticyclone over the heating region. That's a common response of mid-level heating. You have a mid-level heating. On top of that, you have a high increase and an anticyclonic sense. And then you have the teleconnection pattern, the wave number 3 pattern. So it seems like the atmosphere is favorable to produce this wave number 3 pattern that we saw from the cluster analysis. We want to dig into more details of what's actually driving this wave pattern, wave number 3 pattern, and why they're stationary. And sorry for the equation. The name of that equation is way longer than the equation itself. It's the quasi-geostrophic high tendency equation. And it's just a quasi-geostrophic equation that is a prognostic equation for tendencies in geopotential high, denoted by the chi. That's just d phi dt. And I broke it down into terms. The bar is coming from the background state. This is what we use to run the model. And the star is the model response and the anomalies. And you see that maybe we should start explaining panel F. That's just the heating that we prescribe in the model. You see, you have the same structure as the temperature anomaly that I show you related to the monsoon. And red color means tendency to increase the height. So a positive tendency. So this heating will increase the height, causing an anticyclone on the upper level. And the opposite for the blue. And you see that over North America, there's dipoles, blue and red for some terms, and red and blue for the others. And terms like term A, which is planetary vorticity abatement by the anomalous wind, wants to propagate this anomaly westward. But terms such as term B, which is anomalous vorticity abatement by the mean wind, wants to propagate this anomaly eastward. So that's how it turns out to be stationary. And there's very little contribution for the anomalies over North America from term C, which is the main vorticity abatement by the anomalous wind. That's often more stronger on winter months. But in summer months, it's not there, so the pattern tends to be stationary. So term D and E are also competing each other, which is differential temperature abatement by different winds, anomalies or mean. So these patterns are stationary because of these terms. Now, in the more fun part, the statistic analysis, we validate the hypothesis doing the model experiment, but we want to look at the statistics as well. And from observation, panel A, and from model, panel B. This is CESM now. This is the fully coupled model. This is a scatter diagram of the East Asian monsoon index versus the number of heat wave days over the Great Plain. It's not clear cut. You don't have a linear relationship. I'm not expecting to see a linear relationship because there's nothing about linear with precipitation index like the East Asian monsoon. And I'm not expecting a number of heat wave days to be linear either because these are indexed from the tail of the distribution. So from observation and model, you see a good correlation, Pearson correlation, RP and RS is the rank correlation. So when you have a stronger East Asian monsoon, you tend to have more heat wave days. And this is validated with panel C. This is just a PDF, a stochastic skew PDF, which include the skewness and higher moments. For the summer months with weak monsoon versus summer months with strong monsoon, you can see a shift in the PDF, very significant shift in the PDF. And this is not stream, this is all temperatures. And this is for daily mean, that's why it doesn't look as a stream. And panel D shows it's just the count of the number of days as a function of threshold. So I count how many days exceeded a given threshold for these summers, weak monsoon, a strong monsoon, and you see a very distinct signal that when you have a strong monsoon, the threshold increases and the number of days that exceed that threshold also increases. And this is coming from the Pareto distribution. It's a stream value distribution that analyzes return period of extreme events. And again, for weak monsoons, you have a heat wave a heat wave with a daily mean temperature of 30 degrees Celsius, which is a very high temperature for daily mean, every 7 years. Whereas for summers with strong monsoons, that tend to occur every 8 years. So there is a marked difference between the rate of return. So to conclude this part of the talk is we investigated potential drivers of heat wave over the US, and we have identified one as the East Asia monsoon, using observation, state-of-the-art model, as well as a simpler linear baroclinic model. And the mechanism is that you have diabatic heating in the monsoon region that tends to create a upper level anomaly, and that anomaly tends to propagate towards North America across the Pacific as a wave number 3 pattern, which is a preferred wave number 3 unstable pattern in the atmosphere. That tends to set a high pressure dome over the Great Plains, which in turn increases the surface temperature because of lack of cloud, atmospheric land feedbacks because of reduced precipitation. So most of the radiation, incoming radiation over the Great Plain, is used as is turned into a sensible heat flux instead of latent heat flux. This is common in the Great Plain of the US, where the land and atmosphere communicates a lot, land moisture and atmosphere communicates a lot. This high pressure dome tends to stay there for a long time because they're block patterns, and there's very little dissipation associated with it, only radiative cooling above, and that promotes heat wave and droughts. And for future work, this is a paper, fairly old paper now, 2016, that we show. In the beginning of the talk, I mentioned about my motivation for the subseasonal and seasonal prediction of this stream. That's what I show you about the monsoon. But also there's potential for multi-decadal projections of this stream associated with natural variability, not just with climate change. And what we show in this paper is that the MOC, the meridional overturning circulation, especially in the South Atlantic, can actually drive decadal changes of the monsoon, the Northern Hemisphere monsoons. These are the Northern Hemisphere monsoons. This is the East Asian monsoon, and what I'm showing you here is a rank-lag-lead correlation where the South Atlantic MOC and heat transport leads the monsoon on the left part, on the negative lags. And you can see a very clear multi-decadal signal that shows you that when the heat transport in the South Atlantic is weak, you tend to have stronger monsoons about 2 decades later. And that's outlined in this paper, in the 2016 paper, with this interhemispheric mechanism that you see there. So when you have a cold SST because of reduced heat content associated with heat transport divergence in the South Atlantic, you tend to have this interhemispheric circulation, which enhances the northward flux of moisture and the Northern Hemisphere monsoon. And this mechanism is a stretch, how you go from MOC to extreme events. But the South Atlantic is very interesting because that panel in the bottom is just your summer mean, June, July, August, 200 millibar velocity potential in the atmosphere. So what it's telling you is where do you have this Halley circulation. The Halley circulation in textbook is very nice and well driven, just like the MOC in textbook, but it's a little bit more complicated in reality. So what you see for the summer months, you have the upper level divergence associated with the convection over East Asia and North America monsoon. And that has to be balanced by mass balance somewhere else. There has to be sinking motion somewhere else. And that sinking motion is nothing but in the South Atlantic. So if you upset the balance between the atmosphere and surface fluxes between atmosphere and ocean in the South Atlantic, you may upset this interhemispheric circulation. And that's how you can drive these patterns. And this lead time of about 20 years comes from ocean dynamics, by the way. And this is, again, a composite of weak minus a strong South Atlantic MOC 20 years later, a stream function, wave number 3 pattern across the Pacific. And on the bottom, I'm showing you the number of heat wave days with that lead time, multi-decadal lead time, associated with the South Atlantic MOC. And you see, this is a zoom in of that top panel. And the bottom, the color is the number of heat wave days. It's over the Great Plains again. So there is potential for multi-decadal prediction. And that panel on the top, you've seen it. This is just uncertainty due to natural variability associated with the CIMIP models just for the 20th century. And this is the heat waves associated with the MOC in the South Atlantic. And the table shows you the return period of heat waves in the pre-industrial sense. In the 20th century first, every 13 years you get a heat wave. In the pre-industrial sense, you may get one every 73 years, according to the models. And that's for the strong South Atlantic MOC. For the weak South Atlantic MOC, at that lead time, the return period increases significantly from 73 years to 14 years. And that is significant because the random error here is only about plus minus 12 years. So the difference between 73 and 14 is large. So this is part of the future work, assessing the multi-decadal predictability of extreme heat waves associated with the MOC. And I want to thank you all. I will take questions and get some cookies if you want.
We have time for questions. In the audience want to ask a question first?
Yes.
So, Hosmay, you have already an observational long-time series of meridional heat transport in the South Atlantic. When can you go back to the beginning of that time series, see when you had weak meridional heat transport, and see how it relates to actual observations of heat waves?
Yes.
To assess the model. Yeah.
I will repeat the question. Gustavo Goni asked about, we have an observational estimate of the South Atlantic MOC, and we also have observational estimate of heat waves. His question was whether we can go back into the observation of record and validate what we see here from the long lead time multi-decadal that we see from the couple models. And yes, the answer is yes, I have done it. What we have from we have a reconstruction using SST. That's a paper in 2017 that reconstruct the South Atlantic MOC for different latitudes using SST proxies. And we found a very good relationship between, a lag relationship between heat wave events over the Great Plains and the MOC estimation that we have from the reconstruction. The lead time from this reconstruction is about 30 years, not 20 years as the CSM model suggests, but I'm not expecting to get exactly the same lead time from the model and observation because this model have different biases, but at least we see a very clear-cut lead time. It's difficult to look this in observations because you have most of the very strong heat waves occur in the 1920s and 30s during the Dust Bowl. And those are, I believe, to be caused by humans because of poorly managed agricultural over the Great Plains. But excluding those Great Bowl heat waves, we see a good relationship between the reconstructed MOC and about 30 years later, enhanced occurrence of extreme events. But to actually assess that in observational terms, I will have to relax a little bit my definition of heat waves because it's very discriminative. So when I apply this definition of extreme heat wave, it only keeps a very few events. So maybe I may look at some heat waves that just exceed the 90 percentile, for example, instead of 95. But we see a good correlation. Yes.
Yeah, so as a very recent example, over the last roughly 2 weeks, we've had a blocking pattern setting over the U.S., as you know, and that blocking pattern has been largely responsible for this cluster of tornadoes and
Yes.
flooding in the Great Plains region. But you look then at the southeast, and there's the high. I don't know if it's cut off or not,
Yeah.
but producing a lot of heat in the southeast. You look at that pattern, it looks like it's slightly shifted to the east from the pattern you're talking, the omega pattern,
Yes.
at least. And I'm wondering, how sensitive are your definitions to slight skewness in the pattern? Is it still in the category of the pattern you're talking about, or is it different?
Yes, I will repeat the questions. David Enfield asked whether our definition of heat wave is sensitive to a slight shift in the patterns. For example, the very recent patterns last couple of weeks that we've seen over the southeastern U.S. And the answer is, We repeat these patterns using different reanalysis and models, and it's consistent throughout the models. All CIMIC models shows the same clusters, but none of them, including observation, shows a cluster over the southeastern US. So I was a little bogged down by this because I know heat waves occur over the southeastern US, but I guess the large-scale pattern and our definition that we're applying here is not picking those up. It didn't show up on any of the 8 patterns. I just show you 4, but there's actually more. And it tends to favor more like the mid-latitude part, but not in the southeastern US. So I wasn't able to get that cluster. Maybe it's because it's not a cluster, and this is just an sporadic event, very isolated, that doesn't get picked up by the clustering algorithm.
Thank you. Next, let me just pause really quick and see if anybody listening online has a question. Okay, if not, go ahead. Thank you.
So, you had some thought about the relationship between the East Asian monsoon and the Pacific climate variability, such as PDO and ENSO?
ENSO, yes. ENSO is one of the main drivers of interannual variability of the East Asian monsoon. And it's actually a lead. ENSO leads the East Asian monsoon by about 2 seasons. So you have an El Nino and boreal winter that can actually enhance the East Asian monsoon in the next boreal summer because of what's called a Western Pacific subtropical high. This is different from your subtropical high in the Pacific and Atlantic. This is a subtropical high that's only driven by tropical convection associated with El Nino and La Nina. So when you have an El Nino, 2 seasons later, that subtropical high is enhanced, and that actually increases the moisture flux towards the East Asian monsoon. And that could help as a driver of interannual 3 to 6 month prediction of the East Asian monsoon and eventually heat wave.
You're saying that El Nino is more favorable for increased...
The next, yeah, you have it. El Nino. If you have a boreal summer, a boreal winter El Nino, that leads to often, not always, often leads to a Western Pacific subtropical high, which is located southwest of your Northern Pacific subtropical high. That's kind of like an extension, and that actually helps modulate the moisture flux. It's tricky. The East Asian monsoon is tricky because there's another monsoon there that I didn't mention. It's a little south of it. It's called the Western Pacific monsoon, Western North Pacific monsoon, and that's over Indonesia. This is more over Korea, China, and Japan. This is the only monsoon that's extratropical. So the dynamics of that monsoon is a little bit more distinct than any other tropical monsoon. But yes, yeah.
That was my question, if what was the process that gives you the highest predictability for the East Asian monsoon on interannual timescales? It sounds like the MOC is important on
multi-decadal.
So would you say El Nino?
El Nino could be one. Another one is snow cover over the Himalayas. Is shown to play a major role in setting up the background state that, remember when I show you the jet core, is very important for where the convection will occur. And that jet core moves depending on whether you have a snowy season or a lack of a snowy season over the Tibetan Plateau. And that can be predicted because we're talking about monsoon in the summer, and this is often a winter. So that's another one. But as future work, I want to assess the predictability of the monsoon as well.
Do we have any more questions? If not, let's all thank our speaker. Thank you.
Thank you.
And please enjoy cookies on your way out.
Yes.
Those of you
Probably no more peanut butter cookies. So.
You've become very efficient managing these.
Yes. Oh,
I mean, it's much more complicated than it used to be. It used to be you just introduce the speaker and then sit down.
Right. Thanks, buddy.